Okay, so hopefully you just finished the lecture on row echelon forms. The bulk of that lecture was devoted to reduced row echelon form, but we also at the end discussed row echelon form, or you could think of that as non-reduced row echelon form. The rules for both are similar, except the rules for row echelon form are a little less strict than reduced row echelon form. One of the first things that got me into Sage Math, back in the day, I was doing some stuff with reduced row echelon form, and I was looking for some software that would quickly do reduced row echelon form, and I stumbled across Sage Math, and I haven't looked back since. If you want to check whether or not a matrix is in reduced row echelon form, you can use the syntax A equals A dot RREF, open parentheses, close parentheses. So if you're working with a matrix and you want to sort of test yourself, is this thing in reduced row echelon form or not? This code will do it for you. So I have some predefined inputs here. I've defined a matrix, and then I have two print statements. This first print statement will just print out the matrix so we can look at the matrix we input. And the second print statement includes the syntax we just discussed for verifying whether or not something is in reduced row echelon form. So this will tell us whether or not we are in reduced row echelon form or not. So let's click evaluate here and see what happens. So here I've input a 4 by 5 matrix. Let's think through the axioms for a reduced row echelon form together. The first axiom says if there are rows of zeros, that's okay, but they have to be at the bottom. And in this case, that's exactly the case. There's one row of all zeros, but it's at the bottom, so that's cool. Then all of the other rows have to have first non-zero entry equal to 1. So the very first entry of the first row is equal to 1. That's great. The second row starts with 2 zeros, which is fine. But then the first non-zero entry is 1. Also great. And then the third row starts with 3 zeros, which is fine. And then the first non-zero entry is equal to a 1. That's our third pivot. So here we have pivots. As we can see, they move down and to the right. So that's good. And then they are also the only non-zero entries in their respective columns. All 4 of the axioms pass, so this matrix, so we're returning true here. This is in reduced row echelon form. What would happen if I messed around with this matrix I've predefined? So here I've input the rows. What would happen if I took this row of zeros and put it somewhere else in the matrix? So let's take this row of zeros, which initially started here as the last row, and let's say I put it in as the second row. So I'm going to go over here, paste it in, and then reevaluate my code. So now we have the same exact matrix, except now the row of zeros isn't at the bottom. It is now the second row. If we ignored that row, all the axioms for reduced row echelon form would pass. We would have 3 pivots. But there's a row of zeros. It's the second row. So now the code is returning false because we're not in reduced row echelon form. And you could do all sorts of things messing around here just sort of to acquaint yourselves with the axiom. You could just totally delete that row of zeros, but maybe you change one of the pivots from a 1 to a -1. Let's click evaluate. So I've gotten rid of the row of zeros, so I don't have to worry about that anymore. But I've changed the second pivot from a 1 to a -1. And remember, reduced row echelon form is quite strict. To be in reduced row echelon form, you need the pivots to equal 1. So the pivot can equal -1, so this matrix is not in reduced row echelon form, false. So again, if you're curious if something is in reduced row echelon form, you should get familiar with the axioms so you can figure it out yourself, but this should hopefully help you solidify your understanding. The next most important thing we learned were the concepts of rank and nullity. So remember that the rank is the number of pivot columns, and the nullity is the number of non-pivot columns. Or really, rank is just the number of pivots. The nullity is the number of columns that don't have a pivot in them. The syntax for rank is just a.rank, open close parentheses. And the syntax for nullity, as we've defined it, is a.write nullity, open close parentheses. The reason for including the word write here will become apparent as we discuss things like left null spaces later in the course, but we don't need to get into that now. So I've included some predefined code. On the first line here, I'm defining a matrix. And then I have 3 print statements. The first print statement will just tell you the matrix you're working with. The second print statement will tell you the rank. and the third print statement will tell you the nullity. So let's click evaluate. So here, what kind of matrix did I input? Well, it looks like I did input a reduced row echelon form matrix. It looks like it has 4 rows and 1, 2, 3, 4, 5 columns. Where are the pivots? The pivots are in the 1, 1 position, the 2, 3 position right here, and the 3, 4 position right here. So we have 3 pivots, which means the rank has to equal 3. There's 3 pivot columns, and that's true. The rank is equal to 3. What about the nullity? The nullity is the number of non-pivot columns. And so here we had 3 pivot columns, and then there were 2 columns that didn't have pivots in them. So the nullity had to equal 2 here. So that's pretty cool. So again, if you're trying to familiarize yourself with all, how all this stuff works, sometimes it's useful just to have something do calculations for you, so you can just do some sanity check, make sure that you're understanding everything. Finally, the last thing we discussed was the concept of a matrix being in row echelon form. Row echelon form is the same thing as reduced row echelon form, except 2 key differences. The pivots don't have to equal 1, and you're allowed to have non-zero entries above pivots. So here I've predefined some code, and the first line is just a matrix that I've predefined. And Sage doesn't have predefined syntax to check whether or not something is in row echelon form. And there are various reasons for this, so I don't think we need to go into it. But I went ahead and just coded something quick that will check it. This is definitely not the most efficient thing you can do, but it's pretty good. Here, basically what's going to happen is I've input my matrix. I've written a function here that will determine whether or not the matrix is in row echelon form. And then I have 2 print statements at the bottom here, if you scroll down. The first print statement will tell you the matrix you input, and then the second print statement will answer the question, is this matrix in row echelon form? And then it'll apply the function I wrote here. So let's click evaluate. So here, what kind of matrix did I input? It looks like I input another 4 by 5 matrix. There's a row of zeros, but it's at the bottom, so that's fine. The pivots look like they're equal to a 2, a 3, and a -4 here. They're not equal to 1, but that's cool because I'm only looking for row echelon form, not reduced row echelon form. And you'll notice that for the second and third pivots, there are non-zero numbers above, but not non-zero numbers below. This matrix is definitely in row echelon form, and that's confirmed by the statement here. Is A in row echelon form? The answer here is true. What would happen if we mess this up? So what if I change this 0 to a 1 here? Well, if I wrote my code correctly, this should return false. Oh, no, that actually just puts a pivot in a new position. That doesn't mess anything up. So that 1 doesn't change anything. We're still in row echelon form. So no, I just added a 1 in a position here. And since I messed with it, I figured that might change things, but it actually doesn't. We have a row of zeros, and the pivot positions are now in the 1, 1, the 2, 2 position, and then the 3, 3 position. But if I add any number before that 1, that should mess things up. So let's click evaluate. So now the answer is false. This is not in row echelon form. We have pivots at the 1, 1 position, this 2, and then this 2, 2 position where there's a 3. And remember, pivots can't have non-zero numbers below them, so this 1 is messing us up here that I just input. So this is not in row echelon form. I don't think there's anything else to include computationally from this lecture. So not a ton of calculation here, more just a few things to help solidify your understanding. That's the rest of the week, I guess. So thanks for